Okay, so start by recalling the work of Anton Good, from 1980, probably 81. And so he considered if a holomorphic primitive form for SL2Z, and he established the bound that if you look at L half plus IT, so T is going to be real, of course, of F, then it's bounded by, so his first bound was T to the power 5 by 12 plus epsilon. The implied constant here depends on the form F and epsilon. So it's for any epsilon greater than 0. Okay, and I'm going to take T to be larger than 3 to avoid some pathology. Anyway, so later he improved this to, I think, 1/3. So the convexity bound in this case is T to the power 1/2, which follows from the functional equation of the L function, right? So this is the first instance of a subconvexity in the case of a GL2L function. So let me also write it later. It was improved to T to the power 1/3 plus epsilon. The exponent 1/3 is particularly nice because it's the wild exponent, the subconvexity, right? And the other thing that I want to recall is the work of Duke, Friedlander, and Ivanich. It's from around 1990, so roughly 10 years after Good. And they worked with same F, holomorphic primitive for SL2Z of some weight K, and let chi be a Dirichlet character, primitive modulo D, and look at the twisted L function at the center, 1/2. So for me, all the center is 1/2 always. It doesn't depend on the weight. It's normalized, right? So L half of F twisted by chi is bounded by the discriminant. So again, the discriminant to the power 1/2 is the convexity bound, and they improved it by 1 by 22 plus epsilon. Okay, again, the implied constant here depends both on epsilon and the form F. Okay, so this is the analog in the GL2 case of the famous Burgess bound, but the exponent is not that good as Burgess. Anyway, okay, so these results have been improved. For example, this has been established for all mass forms, not just holomorphic forms, for any level, any weight. And moreover, we now know that some subconvexity bounds, even in the case of number fields. So I understand my voice is sometimes going and then going down and going up. It's okay. It feels like that from here. Anyway. Okay, so for example, one improvement is as maybe I just draw. So now we know even hybrid bounds like this. If you look at half plus IT and F twisted by chi, then the conductor. So you want to bound in terms of both D and T, and now we know something like it's bounded by 1/2, which is the convexity minus 1 minus 2 theta by 8 plus epsilon. So where theta over here is the exponent towards Ramanujan conjecture for mass form. Okay, and this is it follows from the work of Michel and Venkatesh, and they actually don't compute the exponent. It was computed by their student. What was his name? Maybe ooh, I think, ooh, what's the name? Ooh, I guess it's, yeah, it's ooh. Maybe Jew. Maybe, ooh, yeah, okay. Anyway, so so if you assume Ramanujan, so theta is going to be 0, and then it's 1/2 minus 1/8, which will correspond to the Burgers exponent in this case. So the bound is as strong as Burgers. All right, so this has been proved in a different way using ergodic theory. But the initial approach by Good and Diffie-Landry-Ivanich was based on moment computation. Okay, so I'll now like to recall how they proved this. So the method so you compute the second moment of certain L functions in certain families. So what Good did is he computed the integral from 0 to t, L½ plus it squared dt. So it's the second moment of the L function, which is same as the fourth moment, analogous to the fourth moment of Riemann-Zeta function. And he showed that this is asymptotically t times p1 log t plus an error term of size t to the power 5/6 log t to the power 13/6. Okay, where p1 is a polynomial of degree 1. So 1 here means that degree is 1. So there's a term with log t, and there's a term without log t. Okay, and the exponent 5/12 comes from the error term because you have 5/6, and you have square over here, and so you have to take square root of 5/6, which is 5/12. Okay. So how do you compute? How do you prove such a result? So as Koenig did, we look at the approximate functional equation. So we have an expression of L½ plus it if some sort of a, which is not exactly equality. It looks like something like lambda fn. So lambda fn is the normalized Fourier coefficient by n to the power 1/2 plus it. Then there will be some weights over there, which I'm going to ignore. And the weight will say that the tail contribution is small. Okay, so the tail, whenever n is larger than the square root of the conductor of this is t squared. So if it's larger than t, then it's going to be small. Okay, so n roughly goes up to t to the power 1 plus epsilon. There is some analytic weight over here, and then there is another part which comes from the other side of the approximate functional equation. So in this case, if you look at full level, then you know about root number, so you can write it down very easily. So to compute the second moment, so you have to compute the second moment of such expression. So if you look at the integral 0 to t of the sum lambda fn n to the power 1/2 plus it square, where n goes up to t, so t is positive. And then you open the absolute square, and then you do the integral. Okay, so you have a double sum over n and m going up to t, lambda fn by square root of n m, and then an integral from 0 to t, something like n by m to the power it dt. Okay, so it's an oscillating integral, and it will be small if the distance between n and m is larger than t to the power epsilon. Okay, so you'll end up with a shifted convolution sum. Which looks like lambda fn plus h. So h is fixed, the length of n is roughly like t, and you find out that if you put the trivial bound here, you recover the convexity bound. So you have to get something non-trivial in this case. So actually he computes the asymptotic of this, right? So this is how he proves it. And the way he tackles this is, so you tackle it using spectral theory of point-carrier series. Okay, because if you look at the corresponding Dirichlet series, then it can be written as an integral with the point-carrier series and f square, right? So then you use the spectral expansion of the point-carrier series to investigate such an integral. Okay, so that was roughly the proof of Goods asymptotic. And from the asymptotic, you can recover the bound for an individual term in the following manner. Okay, so you have a expression. You can always write the. So let me. So you can write square of L half plus IT f as a integral, as a contour integral over some epsilon L square half plus I t plus some s f gamma s plus ds plus corresponding term with minus s, right? You can do this. This is the contour integration representation. And so that's a way to move from an individual term to an integral. Okay? And from here, using things like Stirling to take care of the gamma function, and what else? You need functional equation, and finally Cauchy. You end up with an expression of the form that L half plus IT f absolute value square is bounded by 1 by epsilon square, an integral from minus 1 by epsilon to 1 by epsilon, absolute value of L half plus I t plus tau, say, f square d tau plus 1. Okay? And so where epsilon is like 1 by log t. And now you can write this integral as an integral. So the t goes up to 1 by, the tau goes up to 1 by epsilon. So t plus tau goes up to t plus 1 by epsilon. So there's an integral from 0 to t plus 1 by epsilon minus an integral which goes from 0 to t minus 1 by epsilon. And for them, you use the asymptotic. The main term cancels, and you're left with the error term. So you get a bound of this. This is bounded by this guy. Okay, and then you take the square root. So that's how you end up here. You can actually replace the epsilon by log t to the power 13 by 12. Okay, so that's basically the proof of Goods' theorem. So the method of Diouvre-Friedlander advantage is similar. It is based again on a computation of second moment. But in case of a twist by a character, you cannot expect a formula like this. So it cannot be as simple as this. This is an analytic formula. You cannot have an arithmetic. We don't have an arithmetic analog of such a function formula. So what they do is they look at second moment. So this DFI method. So again, you have an approximate functional equation which says that this twisted L value is roughly bounded by d to the power epsilon supremum of s chi n by square root of n, where n goes up to d to the power 1 plus epsilon. Okay, this is what you get from the approximate functional equation, where s chi n is the sum of the form lambda f n chi n with a smooth weight Vn by capital N. N runs from 1 to infinity. Okay? So I'm ignoring the tail because the tail will make a small contribution, and you're left with a sum with going up to d to the power 1 by epsilon, which I'm just breaking into dyadic, smooth dyadic subdivision, okay? And you get something like that. So this follows from approximate functional equation. So the problem now reduces to getting bounds for this type of sums, okay? So for that, they look at a moment, so they consider SI n square, and the second moment over all psi modulo d. So in their case, they take d to be prime for simplicity, because here you actually need to take, no, it's okay, I think it's okay. So let's take psi modulo d, and then they try to get upper bound for that. But you'll see that even if you prove Lindelof on average for this sums, you only get the convexity. Okay, so that's the usual case for GL2, that if you compute the second moment, you end up at the boundary, and then you need to amplify a bit. Okay, so chi is one of those psi's, and so you want to put a weight over here, says that for psi equals to chi, the contribution is given a bigger weight, right? So you put a weight lambda L psi L square of length capital L, and you want this sum to be large for psi equals to chi, so you take lambda L to be chi L bar, so that it becomes 1. Okay, otherwise there will be, you expect a square root cancellation for this. And then they show that this is bounded by dn L to the power 1 plus epsilon plus ln to the power 7/4 plus epsilon L squared. So this is the diagonal contribution. This is of the diagonal contribution. And now you drop all the terms except psi equals to chi, for which this is of size L square. Then you divide by L square. This becomes ln to the power 7/4, which is already smaller than the trivial one. And here you have dn to the power 1 plus epsilon by L. And that is L better than the convexity. And this is how they prove their bound. And so you have to just optimally choose your L, and that will give you 1 by 22 over here. Okay, so that's basically how they do the GL2 case of subconvexity, computing moments. Okay, so now after the work of Michel and Venkatesh, there is not much remains to be done in the case of GL2, except like improving, yeah.
Actually, that result has been improved. The hybrid has been improved. It's now.
This one?
Yeah.
Yeah. What?
A recent improvement to that.
John Bart.
T to the one. If you assume Ramanujan, T to the 1/3 and D to the 3/8.
T to the power 1/3. So while in T and
T to the 1/3, D to the 3/8.
D to the 3/8 is Burgess, and okay, so it's a while in T and Burgess in D. Okay. So that's the best you can do, I guess. Yeah, probably you can. Yeah. All right. So who did it? Your student?
My student. I was looking for a job.
Okay. I don't think I'm that powerful in Tata Institute, but. Anyway, so as I was saying that, yeah, okay, so they're improving the exponent now, so the race is on. Yeah, so the other interesting thing that you can do is instead of looking at SL2Z, then you just move to the higher rank group, SL3Z. And then the things get a little harder. Okay, so let me, I have 15, a little more than 15 minutes, 20 minutes. She doesn't mind. All right, so I'll introduce a degree 3 function. So I'll define what we mean by SL3Z, Hickey mass transform. Okay, so these are going to be functions. These are the analogs of the holomorphic modular forms and the mass forms. And So like in the case of holomorphic forms of mass forms, you have an upper half plane. So we start by defining the analog of the upper half plane. So it's denoted by H3, and it's going to be GL3R modulo the orthogonal group times the scalar matrices. Okay, so that's the analog of the upper half plane. Okay, and we have the USR coordinates. For it, any point in H3 can be represented by uniquely by a matrix of the form y1, y2, y1, x2, x3, y1, x1, 1. Okay. So there, and y1, y2 are positive over here, and xi is the real. Okay, so it's a 5-dimensional space, and so if you look at the universal enveloping algebra at the center of that to find out the invariant operators, and there are two. So those are the analogs of the Laplacian, right? There are two operators who generate the center. One is of order 2, and the other is of order 3. The one with the order 2 looks like y1 square. So I'm not going to write them down. It takes some time. So it starts like this, and then there are 5 more terms. Okay, and delta 2 is far more scary than this, and it's of order 3. Okay, and the center of the universal enveloping algebra is a polynomial ring generated by delta 1 and delta 2. Okay. Okay, so we are going to define Hickey-Mascas forms of some type. So type nu1 and nu2. So these are the spectral parameters. And associated with the spectral parameters, we define the Langlands parameters, because the eigenvalues will be in terms of the Langlands parameters. It's easy to write in terms of Langlands parameters. So alpha 1 is minus nu1 minus twice nu2 plus 1. Alpha 2 is minus nu1 plus nu2. And alpha 3 is 2 nu1 plus nu2 minus 1. So if you add them, it's 0. Okay, and so now we start to define first what do you mean by a mass form, and then we say what is a Mascas form, and then we say what is a Hickey-Mascas form. Okay, so we're looking for functions on this space, complex valued, which is smooth, okay, and which satisfies the automorphy relation that f of g tau equals to f tau for all g in SL3Z. So it's invariant under the action of SL3Z. Secondly, there have to be eigenfunctions of these two operators. So you want delta 1 of f to be lambda of f, and delta 2 f to be mu of f, where lambda and mu can be written in terms of nu1, nu2. So lambda is minus 1 minus alpha 1, alpha 2, minus alpha 2, alpha 3, minus alpha 3, alpha 1, and mu is minus alpha 1, alpha 2, alpha 3. Okay, so, and then it has to satisfy a certain growth condition. It says that there exist n1 and 2 such that the function f at y1, y2, y11 times y1 to the power n1, y2 to the power n2 is bounded in a domain y1, y2 greater than 1, for example. Okay. So any function that satisfies these three conditions is called a mass form of type nu1, nu2. And for cuspidality, we call it as cusp form if the periods vanish. So there is a double integral from 0 to 1, f1, xi3, 1, xi1, 1. So as always, the missing terms in the matrix are zeros, right? So d xi1, z xi3 equals to 0, and integral, same thing there. We have 1, xi2, xi3, 1, 1, tau d xi 2 d xi 3 equals to 0. This is for all tau. Okay, so that's the definition of a mass cost form of type nu1, nu2. And now to introduce arithmetic, we define Hickey operators. I'll just tell you in 1 second what it is. So we have Hickey operators are coming from double cosets, right? So as usual, so we define, so there will be a Tn and Sn and Rn, and I'm just going to write down what Tn is. So Tn is going to come from a double coset of the form. So gamma is my SL3Z. So it's going to be, all right, so this is a sum over all factorizations of n of the form n naught cube n1 square n2 equals to n, and gamma n naught n1 n2 n naught n1 n naught gamma, and the action, and then you have some Sn, which is defined the same way, and there's an Rn, which is defined the same way, and the Hickey algebra for the prime P is the ring generated by Tn, Sn, Rn, and the Hickey algebra is the internal tensor product of HP over all primes. It's the Hickey algebra, right? And the nice thing about Hickey algebra, okay, so if you start with the space of mass cost forms of a given type, then these operators act on that space. And it is a commutative algebra of normalized operators. Okay, so that space will have a basis consisting of simultaneous eigenfunctions of all the Hickey operators. Okay, they also commute with these two operators. Okay, so that's how you end up with a basis of functions which satisfy all these. Moreover, they are eigenfunctions of all the Hickey operators. Okay, and that's the definition of a Hickey mass cost form for SL3Z. Okay, and the nice thing, well, then they have a Fourier expansion. So this is the last thing you need, or a Whittaker Fourier expansion, which looks like, so f of tau. So there will be a double sum over n1, n2 from 1 to infinity, lambda n1, n2, so some complex numbers, n1, n2, and then there's a sum over g over gamma infinity 2 and gamma 2, so I'll tell you what gamma 2 is. Then we have the Jackie-Whittaker function, nu1, nu2, of type nu1, nu2, n1, n2, n1, 1, g tau. Okay? And gamma 2 is a subgroup of SL3Z consisting of matrices of the form. Okay, so ABCD1. Okay? And gamma infinity is the intersection of gamma infinity and gamma 2, where gamma infinity is the subgroup of upper triangular matrices, right? Okay, that's the Fourier expansion. This is a Jackie-Whittaker function. I'm not going to write down what they are. You can write it as a Mellin-Barnes integral of 6 gamma factors. And these guys over here are called the Fourier coefficients. Okay, so these are the interesting things to study. And so if you start with the Hickey mass cost form, then these Fourier coefficients have some arithmetic structure. They are multiplicative and all that. All right, so now we can define an L function for any such f. So L function associated with f is defined as by the Dirichlet series lambda 1n by n to the power s, n runs from 1 to infinity. And this also has a Euler product because it's a Hickey form, there is a multiplicativity relation. It's lambda 1p, p to the power minus s, plus lambda p1, p to the power minus 2s, minus p to the power minus 3s inverse. Okay? And we can also define the twisted. So if you start with a chi as before, primitive character modulo d, we define the twisted function by chi n by n to the power s, and runs from 1 to infinity. It also has an Euler product of similar type. Okay? So one can prove that they have analytic continuation. So a priori they're absolutely converging for sigma greater than 1, sigma real part of S. And they have analytic continuation and functional equation. Okay, and it follows okay, let me see. I can go with this. Right, so you have, so the trivial bound or the convexity bound, in this case is, if you look at L half plus IT, if twisted by chi, then it is d times absolute value of p to the power 3, 4. Okay, 3 is the, to the power 3 is the conductor, so 1/4 of the conductor. Plus epsilon, if you want to write an epsilon here, you can write, otherwise you may just drop it. So a special case of such L function of degree 3 comes from GL2 ellipse. Okay? So if you start with a GL2 form, if you write on the L functions, it write a Euler product. The Euler product splits is a degree 2. So there's alpha FP and beta FP, where F is small f. Yeah, it's a GL2. And then you can construct a degree 3 Euler product from there. For SL to Z, it's just 1. Minus 1 is a degree 3 of function, and this corresponds to a GL3. This comes from a GL3 Hickey-Moscas form. Okay? So these are called GL2 ellipse, or the symmetric square. So if here is say an SL2Z mass holomorphic or mass form, and then this is just LS of symmetric square of F. Okay, so for this, there has been some work due to Lee and Valentin Blomer. So Lee solved the T aspects of convexity for such a function. She proved that L half plus IT of sim square, F where F is SL to Z, is bounded by T to the power 3/4, which is minus 1 by 16 plus epsilon. And Valentin proved that L half sim square F twisted by chi is bounded by d to the power 3/4 minus 1 by 8 plus epsilon. Okay? But here the condition that chi is quadratic. Okay, why he needs quadratic? Because it's essential in their case that these L functions are self-dual, because they need the central values to be non-negative. Non-negativity of the central value, which was proved by Lapid. Anyway, so the moral of the story, if you try to compute the second moment, because for subconvexity you usually need the second moment, it turns out to be very hard. So no one knows how to compute the moment in the general case. But nevertheless, in some special cases of this special case, you can compute the second moment. Okay? So the first theorem, say chi is primitive modulo p cubed p prime. You can actually do it for any prime power except prime of just prime. okay, prime square and so on. You can prove it. And it's L half sim square f twisted by chi. Okay, so p to the power 9/4 is the convexity. You can prove minus 1/4 plus epsilon. Theorem 2. Now if you take, so here this depends upon epsilon and f. If you take chi to be modulo p to the power L, and you fix p and take L towards infinity, okay? So it's like the non-Archimedean analog of the T aspects of convexity. Okay? It's just ramified at one place. Okay? In this case, you can prove that L half sim square f twisted by chi is now the bound here depends upon epsilon, f, and p, but doesn't depend upon L. Okay, so you can show that this is p to the power 3 L by 1/4 is the convexity, but you can have a saving of 1/36 plus epsilon. Okay, but still, the nice thing here is that you don't need chi to be quadratic, so they need not be self-dual. But still, they are just lifts of GL2 function. And now I just had some fresh results. Theorem 3. So I don't have time to prove that. So f L half plus IT f is bounded by e to the power 3/4 minus 1/32 plus epsilon for any f not necessarily symmetric square. So it settles the GL3 subconvexity in the 3D aspect. Theorem 4, L half f twisted by chi is bounded by d to the power 3/4 minus 1/4152 plus epsilon. It doesn't matter what you have here, but here we assume d prime. This is just a technical convenience. You can do it for all d, I'm sure. And but you have to assume the Ramanujan conjecture, the full strength of Ramanujan conjecture. That means that the Fourier coefficients are bounded by divisive function, and the Langlands parameters are on the half line. Then you can get subconvexity. So in particular, if you take f to be symmetric square of a holomorphic form, for which you know already, then you have this unconditionally for any chi, not necessarily quadratic. Okay, so that extends the result of Blomer. And I have no time to present the proof. Okay, thank you.